So my name is Mohammed Emtiyaz Khan, but just please call me MT because it's easier to remember for you. And this is me from the time when I had a little bit more hair. So now I work at, I run a team on Approximate Bayesian Inference at the Ricken Center for AI project. And let me actually start the timer so that I know that I am not going over time. Reset. All right. So today I'm going to just summarize some of the work that we have done in my team in the last 2-3 years. I'm going to talk about fast yet simple natural gradient descent for variational inference. Okay, so the goal of variational inference is to be able to approximate the posterior distribution by using optimization algorithm. And this strategy has been extremely popular in many subfields of machine learning, and it's been used quite a lot. But for variational inference algorithm to be truly successful in these applications, what we really need is that we want our algorithms to have some desirable features. So we want our algorithms to be general so that they apply to many variety of models. They should be scaling well to large data and large models. They should converge very quickly, and they should be easy to implement, execute, and deploy, etc., etc. So in this talk, my hope is to present some new algorithms that have this type of features. And what I'm going to do is I'm going to basically focus on some improvement. I would like to improve the existing modern gradient descent methods, such as those that use stochastic and automatic gradients. Basically, these methods are designed to focus on deep learning type of applications. So they're extremely simple, general, and scalable. But then they have, because they are first-order gradient methods, they can have suboptimal convergence rate. So my hope is to sort of improve this. And what I'm going to focus on today is a type of method called natural gradient descent method that by construction is supposed to have a faster convergence rate than gradient descent methods. But then if you want to apply them to deep learning models, then they have computational difficulty. So it makes their application to complex model quite difficult. Okay, so my hope is to show you some new algorithms such that we can perform natural gradient descent in a simple way while preserving the fast convergence that comes with it. And then I would like to be applied to deep learning applications. Okay. So that's the goal. So what I'm going to do, I'm going to start with some background on variational inference with gradient descent and natural gradient descent. And then I'm going to present a new method to perform natural gradient descent with this method called conjugate computation variational inference that we proposed 2 years ago. And basically what this method does is that when you apply to a conjugate or a conditionally conjugate model, it reduces to well-known algorithms like forward-backward algorithm or stochastic variational inference and variational message passing. But then it extends the use of these algorithms to models that are not conjugate. So something like models containing deep network in it, right? So it's something like what Thomas was actually talking about before. It's an algorithm that reduces to the optimal algorithm, depending on what kind of model you give. So I'll conclude in the end with some generalization and extension, but let me start with the background on variational inference, how you can use gradient descent and natural gradient descent for it. Okay, so the goal is to approximate the posterior distribution, and the unknown that could be parameters or it could be latent variable, and I denote it here by theta. And I want to estimate this posterior distribution given the, I want to estimate the posterior distribution given the data d, and the parameter is theta. So in variational inference, we approximate it by a fixed form variational inference. So I'm going to, throughout the talk, I'm going to assume that this is an exponential family approximation with some natural parameter lambda. And now my goal is to estimate this lambda such that the distance between the approximation and the exact posterior is minimized, right? So basically you can do this by maximizing the evidence lower bound, and we all know this. and then you can compute the gradient of this, and then you can take a step in the direction of the gradient. Right? So it's going to give you a lambda such that it's optimal in some sense. All right, so natural gradient descent is slightly different. In natural gradient descent, you're preconditioning the gradient with the Fisher, inverse of the Fisher information matrix of your variational approximation. So what happens as a consequence of this preconditioning basically allows natural gradient descent to optimize in a Riemannian manifold instead of a Euclidean space. Right? So when you're taking steps, you're actually measuring the distance between these steps, not by simply just, if you're doing Euclidean space, then you're measuring the distance between these parameters individually. But if you're doing optimization in the Riemannian manifold, then you're measuring the distance between the distribution directly. Right? So this sort of, by construction, has the right kind of property, and it should help you to give fast convergence. And I'll show you some simple example which will convince you that this is like Newton method, and this will converge faster. Okay. But the problem with these iterations that now it requires additional computation, right? So you have to compute the Fisher matrix, you have to invert it, you have to multiply it. So it should be more expensive than doing gradient descent. So the question is, can we simplify or reduce this computation while maintaining the fast convergence that comes with it, right? So that's the question that I'm going to answer in the next few minutes. Basically what I'm going to show is that yes, you can do so. You can convert the natural gradient descent computation to well-known algorithms like message passing and backpropagation. Okay, and it's done by this algorithm called conjugate computation variational inference. So anybody has any question? All right, super clear or completely unclear, right?
You mentioned that you were using the exponential family earlier.
Yes.
But I think you also said something about the model was not specific to, this approach was not specific to a specific family of...
Oh, so the model could be anything.
Okay.
The approximation family has to be exponential. Thank you. All right, so let me now get into the detail of this method. But the key idea in this method is to use a different type of parameterization. So instead of using natural parameter of exponential family, now we want to use something that's called expectation parameter. So every exponential family has this quantity associated with it. This is called sufficient statistics. And if you take the expectation of it, then you would get the expectation parameter. This is also the moment or the mean parameter, right? So if you don't remember these details, then just think of like Gaussian distribution. Suppose the mean is m and the covariance is v, then the two moments are basically mean and the correlation matrix. Okay? So why this is useful is because this gives us an alternate way to compute natural gradient. Basically, the key relationship is that if you want to compute natural gradient with respect to natural parameters, then you can compute it by just computing gradient with respect to expectation parameter. And this happens because of the duality between the expectation parameter space and the natural parameter space. And this relationship has been actually known for a while. And you can actually, if you substitute this in the natural gradient update, it just gives you a very simple update where you're performing the gradient updates in the natural parameter space, but your gradient computation happens in the expectation parameter space. So what we do in our paper is basically we start with this idea and then we show that this step actually is equivalent for conjugate models. It's equivalent to just simply adding the natural parameters that you have in your model. Okay, so it's basically like if you have two conjugate distributions and you multiply them, then equivalently you add their natural parameter in the exponential. And this is type of computation in Bayesian statistics. It's called conjugate computation. And many conjugate models have this kind of form where you multiply, for example, two Gaussians, and you just add their natural parameters together and you'll get the resulting thing, right? So I don't have time to really go into the detail of what conjugate computation is, but what I'm going to do is I'm just going to show you a simple example on a conjugate model. Then I'll talk about conditionally conjugate models, and then I'll talk about non-conjugate models. Okay. All right, so let me start with a very, very simple example, Bayesian linear regression. Yes?
Can you go back to the previous one? Do lambda and mu have the same size?
Yes.
Do they have to have the same size always for any exponential thing?
That's a good question. So there's a restriction here that it has to be minimal exponential family. And when it's minimal, then the Fisher information matrix is invertible and just a square. That is fine. Thank you for asking that question because I always leave the technical detail here. So that's a restriction. All right. So, okay, so linear regression, Bayesian linear regression. So the likelihood is just a quadratic. Y is the output vector, X is the input matrix, and theta is the weights here. Okay? And my prior is Gaussian, right? So now I want to perform variational inference on this, right? So then I'll have to start with an approximation. I'm going to choose it to be Gaussian with the mean M and the covariance V. This is going to be exact because Bayesian linear regression, the posterior is Gaussian. Okay? So I can write the variational lower bound. I subtract this approximation, and then I take the expectation. This is the variational lower bound. And then my goal is now to compute the natural gradient with respect to the expectation parameter. Right? So I have the mean and the correlation, and I want to compute the gradient. And if I do that, then I'll get the natural gradient. So here is the cool thing. It's that because this is theta and theta transpose, you see that this is actually at most quadratic in theta, right? So if you actually take this first term and you sort of simplify it, then you can write it as a function of the mean parameter. It's basically, expectation parameter. So it's linear in the expectation parameter. Okay, so the term that's the coefficient that's in front of theta is going to be the gradient with respect to that, and the term that's in front of theta transpose is going to be gradient with respect to the expectation parameter. Right? So if I do that for this first term, I'll just get that. Right? So it's super simple. Same thing here, there's no linear term, there's only quadratic term, so I get something here. And you can look into my paper, and this is also actually is there in the SBI paper also. You take the gradient of this, you get the natural parameter of the cube. Okay? So basically what you're doing, you have natural parameter of this, the natural parameter of this, and natural parameter of this. And you're just adding them together. Okay? So if you add natural parameters together, you compute natural gradients. Right? So it's very, very simple. And now you have to substitute that into the natural gradient update. And once you do that and you simplify, then you'll get some update like this. Basically, your mean is a convex sum of your previous mean and the least square solution. Right? So if you set rho equals 1, the step size, then you'll just converge in one step. Right? So it's a Newton step. For linear regression, if I do natural gradient descent on variational on elbow, then it's equal to least square step. It's a Newton step. Okay, so it will converge optimally in one step. But if you did gradient descent, it's going to take many iterations. This is quadratic. It'll take many iterations to converge. Right? So this is actually a really, really nice property that natural gradient is actually giving you the optimal algorithm that you need, but gradient descent is not. And this property generalizes to all conjugate models because the elbow is linear in the expectation parameter. Okay, you can just take the gradient and you'll get, essentially you'll get forward-backward algorithm by using natural gradient descent. Okay? So basically the result is that natural gradient of elbow can be computed by using forward-backward or forward-backward algorithm on the conjugate model. Okay? So now let's go to a conditionally conjugate model, and for this usually you have this kind of graphical structure, so you can then assume a mean field approximation, and then you can do some mean field update here, and it's very, very similar to the thing that I showed before. So you set the step size to be 1, this mean field update corresponds to the forward-backward algorithm. Okay, so it's variational message passing is actually doing natural gradient descent with the step size of 1. And this is actually known, many people have written about this, and SVI is very similar to this. SVI is doing rho equals 1 for the local variable, and for the global one, it's actually taking more conservative steps. So it's actually not going to the minimum, but rather just doing a natural gradient descent with a smaller step size, right? Because the global needs to move slower, local can move faster. So CVI is sort of a generalization of these methods because now the step size schedule can be anything, and you can do global, local, sequential, parallel, whatever updates you want. So you can show the convergence of this, and we did this in our paper. using stochastic mirror descent framework, you can establish the convergence of this. And this is actually, so I'm running a little bit late, but I'm going to explain this. So here what we show is that, so this was done like 3 years ago, almost. So the step sizes, the steps that you take, they'll be bounded by some term like this, and they're 2 terms. One of the terms with iteration, as it goes to infinity, this goes to 0. Okay? And the other term is due to the stochastic noise. And the most important thing here is this alpha star. This alpha star is the strong convexity parameter of the Fisher matrix. It's basically the eigenvalue, the least eigenvalue. So if it's greater than 1, then you're going to ensure that you're going to convert faster than gradient descent. Okay, so there's theoretical guarantee that this kind of method would actually give faster convergence than gradient descent method if you choose the right geometry and the conditions are all right. Okay. So far I've talked about conjugate and conditionally conjugate, and now I'm going to switch gears and go to non-conjugate model. So suppose if you have deep network in your model, in addition to some conjugate terms, what are you going to do then? Well, I'm going to show you that if I use a Gaussian approximation, then I can simply convert this to a Newton step, and then I can do some approximation to this, and I can write it as an atom optimizer. Okay, so that's what I'm going to show you. Okay, so what I've done here, I've taken the same objective that I've talked before, and I replaced the quadratic thing by a neural network like it. Okay, so X is the input, Y is the output, and this is a neural network. So now I have a non-conjugate term. This is still conjugate because this is Gaussian, and I'm going to assume this to be Gaussian. Okay, so I have conjugate term and non-conjugate term. Okay, so if you have something like this, well, you apply the CVI update, you compute the gradient with respect to the expectation parameter, and if you do that, you'll get something like this that sort of looks very, very complicated to you. But if you compare this to least square solution, you see the similarity. So the update of the mean basically has a solving of a system that looks pretty much like least squares, and the regularizer remains as it is. But then, now you're replacing the Gaussian measurement by a stochastic gradient. So basically, what you do is you sample from your variational distribution. It's like the reparametrization trick. You sample from the variational distribution, then you do backpropagation on the neural network part. It's not the backpropagation on elbow, right? It's just the neural network loss function. And you compute that gradient, and that becomes a Gaussian measurement. So now you can do least squares with it. It's not a linear model, so you don't have the Gram matrix. The Gram matrix is replaced by Hessian. Okay? So the gradient, the Hessian, they give you a quadratic approximation, they give you a Gaussian measurement. So sort of turn it into a conjugate likelihood. So it gives you a local approximation of that neural network as the Gaussian measurement. So it's actually extremely beautiful. And so it's actually quite nice. But then if you want to apply it to large neural network model, then Hessian is going to be like extremely huge. So then we make some approximation here, and we said, so in this paper in ICML this year, we said we're going to use mean field approximation, so we're going to make it a diagonal approximation for the covariance, and then we'll use another approximation of the Hessian. Instead of computing the Hessian, we're just going to replace it by square of the gradient. Okay, this is a very crude approximation, not a very good one. But suppose if we do that, then we can just implement that equation that I showed you in the previous, sorry, it's not my alarm. So this equation you can implement just by using the atom optimizer. Okay, so in atom you compute the gradient by using backpropagation, then you take a gradient step, adapt the learning rate by using scale, yada yada. But my point is that you can sort of make small changes, and we get this method that we call variational atom. You just sort of change 3 lines. It's actually 2 lines. So you add some noise to your parameter, just perturb it slightly, and you get this temporary parameter, and then you run backpropagation on that. Okay. With this simple change, if you continue running this algorithm for some time, then this quantity will converge to the mean, and this quantity will converge to the variance. You can see that this is just gradient times the inverse of the least square thing. So the scale is that matrix. Okay. it's a diagonal in this case because it's mean field. Okay, so even if you haven't got the whole thing here, I'm just going to sort of give you an illustration so that you remember what I was talking about. So here I have logistic regression, two classes, and I'm running Adam and Vadam with iteration. I'm showing the decision boundary. So the Adam always finds one solution, so it's only one line. But what variational Adam algorithm is doing is finding a distribution. So the mean of the distribution is this thick line, and the pink lines are all samples from this distribution. And you see that it's sort of saying that there's no one good solution, because I have infinite solution. This is linear separable case, and I have many lines that could be classifying this data very well, and it's generating that from the distribution that it learns. This is the variational approximation that it has learned. So it knows about the uncertainty that's present in the model, and it's estimating it using variational inference. This is kind of really cool. You can do this on neural network, so you can sort of, you can generate. So that was a logistic regression. Here, Adam returns one line, one decision boundary, and Vadam returns, multiple lines. Just okay. So not only our method is, doing all these things. We show that our method is also faster, simpler, but also more robust. So if you run gradient descent, what we're showing here is this iterations of the algorithm, and this is test error, and we're changing the mini-batch size. So we're sort of going from small mini-batch size to a large mini-batch size. And you see the gradient-based method is actually quite unstable. The noise affects it quite a bit. The natural gradient descent is actually really, really stable. So we have two variants of our natural gradient descent, and the green one is actually really, really stable. It doesn't change. So you see the natural gradient actually gives you some stability here. All right, so this was all on the diagonal, but we have one paper this year at New Rips. I don't know which conference is that. So this method, we call it slang. And what we do here is that we replace the diagonal covariance matrix by low rank plus diagonal covariance matrix. And basically we do this kind of least square step, and we show that all of this can be done in linear time. So it sort of works quite well. I'm not going to go into the detail in this, but the poster is in 2-3 days. You can check that out. But what the kind of results that we get is that if you do some, this is based by backprop, is the mean field method. If you use slang with increasing number of, rank, increasing rank, then you get faster and faster conversion, which is what you would expect, right? Okay, so far I've talked about, non-conjugate model, conditionally conjugate, and the conjugate model. And what I want to just talk about very briefly is the generalization to a general graphical model and then some extensions. So what if you had, a combination of things? So you had like graphical model, but then you put some neural network here and there. What could you do then? Well, so suppose if you have a linear dynamical system here, you have neural network likelihood here. So you would do the least square thing that I showed you. You would sample from your variational approximation, and then given the sample, you'll run backpropagation here, and that'll give you a Gaussian measurement. And once you have the Gaussian measurement, you run forward backward. Right? But you don't take the step size to be 1. You just basically, the marginals that are returned by this forward backward, you use them to take a step in the direction of the gradient. So you don't just set it to 0 and think that you're done, but you're basically doing taking a gradient step. Okay. The same thing here. You run E step of GMM here, and then you do backpropagation here. And it all works out. So this is fairly simple to do if you have all the software. So we also extended this to amortize inference when you have variational autoencoder type of thing, and this builds upon some of David Dubnow's and Matt Johnson's work. Basically, we show that you can do all the same type of thing. How much time do I have? It's kind of scary.
2 minutes.
Okay. Oh, really? Okay. I have lots of time here. Okay, so I'll
do 2 minutes.
Okay, I'll speed up. All right, so you can do everything when you have variational autoencoder. That's basically the point. And you can see the paper, and the DeepMind paper there actually uses some of this stuff. Okay, we also show that whatever I talked about is exponential family, but we can also go beyond that. You can have this kind of property, and this paper here actually does that. takes it beyond exponential family, where you have a mixture of exponential family and other things. Okay, so I'm going to really speed up. So what I showed you in summary is fast yet simple natural gradient descent using this method called conjugate computation variational inference. And when you give it conjugate or conditionally conjugate model, it reduces to existing well-known algorithms. But for non-conjugate models, you can still apply it and get fast and simple natural gradient descent. And I talked about some generalization and extension. But what I really want to talk about is a lot of related work, but I have very little time. But there's a lot of really amazing work that has been done, and our work actually builds upon that. So there's a lot of work done on forward-backward connections to EM and using that for variational inference. So Sato had been actually talking about expectation parameter back in '98. So this relationship was actually known to him. And Mike Jordan and Garamani and others are using this kind of message passing algorithms using local variational bound to compute variational inference. And variational message passing is sort of extension of that. There's a huge work that's done in natural gradient descent, and somehow all of the first authors have names starting with H. So Honkela has been talking about this thing for a long time, and James has actually talked about the relationship with expectation parameter in this paper, and obviously stochastic variational inference uses all of these mechanisms. And very good paper that it's not being appreciated that much is the Sullivan and Nelson. It's a beautiful paper, and you should read it. Hard to read, but it's a really, really nice paper. They come very close to natural gradient, but it's not really natural gradient. It's an approximation to natural gradient, and they're doing some kind of smoothing. Sather Cardon have invented the method very similar to ours around the same time, independently, but this only works for 2-level. Okay. And then Hugh Salamani and James Hansman and others are doing really excellent work for GP and showing that automatic natural gradient can be computed. All right, and then there's some work on Bayesian deep learning, and okay, I have to really speed this up. So, well, some open problems. Should I close or? Okay. It's okay. Lots of work to be done. Good implementation of planes, automatic gradients, some structured approximation, really large problem. Please apply to your problem, big applications. We really need to see if this actually really works in the application, right? So we haven't really done that yet. Okay. So lots of papers. But if you want to read one paper, just read this one. It's a 5-page paper. You can read it very easily. So I've summarized things in this paper. I should thank a lot of people in my team who have done amazing work, and interns and collaborators across the world. Okay, thanks.
I think you did pretty well on time, actually. It's all good. I'm more pushing than necessary. All right, yeah, do we have time for questions? I think let's see. Thank you for the question.
Yeah? Sure, thank you. That was wonderful. Just on the suboptimal problem with the optimization, if the step size is increased, do you have any analysis on the final result?
Sorry, I don't get the question.
Oh, no, it's like the suboptimal problem with optimization. If we use this method, does it have any effect on the final,
If I use the suboptimal method in this method?
Yes.
I don't really know how to answer that question. Can we talk offline afterwards?
Oh, sure. Okay.
I'm sorry.
Maybe another question?
Sorry about
I've been
that.
asking many questions, sorry.
That's all right.
Have you tried quasi-Newton methods instead of Hessian?
Yes, we have. So we spent a lot of time, and we're going to, so one of the intern there who has worked on this, we have tried limited memory methods, and they have an issue when you do stochastic gradient update. They're very unstable, but you can actually make them work. So you will see something in a few months on that.
One more?
In lots of these deep learning applications, people study the kinds of local optimum that they find, and they hypothesize about sharp and shallow local minimum. Do you find that the natural gradient method gives you different? Do you fall at different local minimums, or do they have the same problem?
That's a hard question, and I do have some insight on this. But so we have worked, so you can see variational inference is something that I didn't realize before. You can see variational inference as a smoothing of your loss function. So it's like an expectation of your loss. So you're sampling from your variational approximation, and you're sort of smoothing the objective function by averaging over many samples. So that has a tendency that it sort of makes the objective function a little bit more regular. Right? But with that, if you apply this to like evolution strategy or something like that, there we sort of see that natural gradients, the covariance of your variational distribution is actually measuring how wide or shallow, sharp your minima is. So we have an archive paper on this, where we apply it to natural evolution strategy. And you directly see that the covariance is related to the Hessian. And so if you sample the Hessian and it's a wide thing, then the algorithm will stabilize there more than some other place. So it has that property, but not for variational inference, but for evolution strategy.
All right. Well, let's thank the speaker again. And so now we're coming to the last contributor talk of this session. We have Matt Hoffman on neutralizing bad